Astronomers have discovered a mysterious cosmic object that shines about 10 million times brighter than the Sun. This puzzling object seems to defy a basic principle of astrophysics. To put it into perspective, the object is so bright that if it were placed 474 billion kilometers away from us, or about 3,100 times the Earth-Sun distance, it would still appear as bright as the Sun does during daytime. The object puzzled astronomers because not only does it produce enormous energy, but it also shines 100 to 500 times brighter than what the previously known laws of physics permit. However, when they studied it in detail, they stumbled upon new physics that added to our knowledge of how the universe works. So what exactly is this object that's shining so brightly? What's the mechanism behind the tremendous energy output from this object? Finally, and most importantly, how has this finding opened doors to new physics? When a compact object like a neutron star or black hole gets close to a star in a binary system, something interesting happens. The strong gravity of the compact object pulls matter from the star towards its core. However, because of angular momentum conservation, the matter retains some angular momentum and doesn't fall directly into the core. Instead, it forms a swirling disk around the compact object, called an accretion disk. As the particles in the disk lose their gravitational potential energy, they get hotter and emit thermal radiation across a wide range of wavelengths. For black hole accretion disks, this radiation is usually in the form of X-rays. An accreting object can only shine up to a certain point called the Eddington limit. This limit is determined by a simple rule known as the Eddington rule. When matter falls into the black hole and produces radiation, the outward pressure from the radiation pushes against the inward pull of gravity. When the radiation pressure becomes stronger than gravity, the matter stops falling in and the luminosity reaches its maximum level. This maximum luminosity is referred to as the Eddington luminosity, since it happens when the black hole can't pull in any more material. Basically, the stuff going into the black hole determines how bright it is, and it reaches its brightest point when nothing else can fall in, following the Eddington limit. Once we know the black hole's mass, we can easily calculate its maximum brightness using a specific equation. But as our sky surveys improved, we started discovering objects that exceeded the Eddington limit by a significant factor of 100 to 500. These objects were named ultraluminous X-ray sources, or ULXs for short. At first, astronomers thought these ULXs contained black holes at their centers, pulling in matter and shining brightly. But the exceptionally high luminosity observed in ULXs puzzled scientists, prompting them to investigate the driving mechanisms behind these mysterious sources. To unravel their secrets, scientists focused on one particular ULX called M82X2. This ULX is located in the Cigar Galaxy, about 12 million light-years away from us. What makes M82X2 unique is that it contains a special kind of object called a pulsating neutron star, also known as a pulsar, as the one doing the accretion. It enabled astronomers to solve the mystery of this class of objects. The key question that arises in the case of a ULX is why this source shines with such extraordinary brightness. As previously mentioned, during accretion, the transfer of mass fuels the surge in luminosity. Ordinarily, the accretion and accompanying luminosity surge would stop once the object reaches the Eddington luminosity. However, this does not hold true for M82X2 and its counterparts. And scientists have put forth two potential scenarios to explain this intriguing anomaly. One would naturally think that if there is a surge in luminosity, then a large amount of matter is being transferred to the pulsar from another object. However, there is an alternative explanation that suggests the brightness could be caused by a small amount of matter being transferred at a slow rate. In this case, most of the matter forms a cone shape that points directly towards us or is aligned with our line of sight. The relativistic effects of this concentrated matter make this system appear even brighter than it actually is. This phenomenon is called geometrical beaming, where the observed brightness exceeds the actual brightness because the material is moving towards us at relativistic speeds. However, there is a limitation to this scenario. The model proposing geometrical beaming assumes that the X-ray pulsar has a magnetic field strength of about 10 billion Gauss. If the magnetic field is much stronger, around 10 trillion Gauss, the model no longer applies, and the effect of matter concentration along our line of sight is lost. This difference becomes important in the latter part of the video. To determine which scenario is at play, scientists can directly measure the transfer of matter between the object donating it and the X-ray pulsar. By observing the pulsar's motion in its orbit from 2013 to 2020, astronomers identified a specific point in the pulsar's orbit where the time it took to cross that point gradually decreased over a period of 7 years. Now, this is a very important sign of mass transfer. Through calculations, scientists determine the amount of mass being transferred from the massive donor to the pulsar, expressed in solar mass units. The mass transfer rate from the donor to the pulsar is minus 4.7 into 10 raised to the power of minus 6 solar masses per year, where the negative sign denotes a decrease in the mass of the donor object. This corresponds to a mass of approximately 9,300 billion trillion kilograms. In other words, the pulsar is consuming a staggering amount of 9,300 billion trillion kilograms from its companion every year. This mass transfer rate is approximately 200 times higher than the accretion rate predicted by the Eddington limit. Remarkably, the measurement of mass transfer through the orbital decay closely aligns with the mass transfer inferred from observations of M82X2. It is now evident that the extreme mass transfer driven by the massive donor is responsible for the X-ray pulsar shining brighter than expected. Returning to the central question, what is the underlying cause of this phenomenon? How did it break the Eddington limit to become so bright? The answer to this question has led scientists to explore new physics, as the mechanisms driving the mass transfer and luminosity to exceed the Eddington limit require a deeper understanding beyond the conventional understanding of astrophysics. The primary reason for the extreme luminosity observed in X-ray pulsars is attributed to the presence of an exceptionally strong magnetic field. According to one hypothesis proposed in this study, the pulsar possesses an incredibly powerful magnetic field, reaching intensities of around 10 trillion Gauss or 10 billion Tesla. This intense magnetic field exerts a squeezing effect on the matter falling into the accretion disk, transforming the spherically shaped atoms into elongated, stringy, or thread-like structures. Because of this, when the pulsar emits thermal radiation, the photons in the radiation don't push the atoms away as much as they normally would. This allows the matter to keep falling into the pulsar, and as a result, the pulsar can shine even brighter than what the Eddington limit allows. It's also interesting to note that when the magnetic field strength is around 10 trillion Gauss, the collimation effect, which concentrates matter in our line of sight, stops happening. This means that the second scenario of geometrical beaming is no longer valid. Thus, the extreme luminosity observed in ultraluminous X-ray sources is primarily driven by the intense mass transfer, particularly when the accreting object is a highly magnetized neutron star. This discovery is very important because it not only helps us understand more about physics, but also gives us insights into magnetic fields. On Earth, we can't create magnetic fields as strong as the ones found in ultraluminous X-ray pulsars. However, by studying these pulsars, we can learn a lot about how powerful magnetic fields behave. The universe acts like a natural laboratory for us to observe and study things that would be impossible to investigate on Earth. This helps us gain a deep understanding of the fundamental processes that govern our vast cosmos. Recently, astronomers discovered that we significantly underestimated the size of Betelgeuse and its evolution timeline. According to the new studies, the supernova of Betelgeuse could happen within tens of years in our frame of reference. If you missed this episode, be sure to catch up on this exciting discovery.